So this is the damper so far as I have it right now. I've been working on this for probably the last 2 months, just the design of it, from the simple damper as you see down there, just a single degree of freedom structure with plexiglass built in on the sides. Both sides, you move the damper one way, it goes back and forth. And the multiple degree of freedom damper over here, which if you can see, I move it just this way, tilts back and forth, but it has 5 degrees of freedom, 1, 2, 3, 4, 5 down at the base, or next level next to the base, which shows the multiple modes of which this thing can actually oscillate. There's 5 degrees of freedom. For each degree of freedom added to a single degree of freedom system, it seems that there's 2. Grows by a factorial. I can't determine the number right now as what 5 degrees of freedom would have, how many modes it would have. But from those two, this is the damper as I have it right now. I'm trying to model a loft structure, and a loft structure is pretty basic. Let's see, with the small space I have here on the whiteboard, I'll show what I'm trying to model. Some people thought I was trying to model a mezzanine, and that's not exactly what I'm trying to do. A mezzanine is a suspended floor in the middle of another floor. So there'd be one subfloor here, then there'd be the second floor here, and then in between there'd be this middle floor. That would show a mezzanine. This space in here would all be open. This would be locked off. This would be offices or something like that. That's what mezzanines typically are. What I'm trying to do is model a loft structure, which is what you typically see in downtown New York and Chicago and places where people have to live close to work. What they'll do is they'll have an existing building somewhere downtown, and they'll try to build another building inside of that building. Typically this is for the residents, so the model I'm doing is based off of Vincent Gallo's loft in Los Angeles, which is essentially an old and existing warehouse building, and Vincent has, through the use of a stiffening beam, or stiffening ring really, suspended part of another building within this bigger building. And this is where he lives. He lives up here. Here's Happy Vincent Gallo. Hello. Hello world, but his studio's up on top, his bed's down below, and everything else, his living quarters, kitchen, whatnot, is all down on the main floor. So I'm essentially taking this without the ring and modeling the structure as is, as compared to the rest of the building. By doing that, I feel as though I might be able to model fairly closely how a loft structure would behave in a seismic event, which Vincent Gallo's house would probably be subjected to since he's living in California. So as you can see in the model, there's a hole. And the hole, it's the same kind of damper system. You got the top here, and then you got the base. But in the middle, there's a hole, and the hole is actually the loft. This is the loft structure. There's a top, there's an aluminum mass, and then on the top, there's aluminum mass on the bottom, suspended by, it's suspended really inside by, what would be stiffening beams here. I'm modeling that with an angle, which is actually bolted in to plexiglass, which is supporting the sides. The plexi is just to, show how stiff this thing can be in a seismic event. It's to model the oscillation that would occur during a seismic event. And really, the clamps are used to, for these, well, the smaller clamps are used for sensors to kind of indicate how much motion is actually going through the structure at individual points. But this bigger clamp is meant to hold this structure down, so in the event of a seismic earthquake event, it's going to model what the foundation which would be like. In the majority of urban environments, the foundations are pretty strong, pretty stiff, so you kind of want this set really, really rigid. In a seismic event, I take this off and then I subject an impact force here or a free vibration force here. There are 2 tests I'm going to do for each one of them. There's impact and free vibration. I should mention this. Impact test is very, very straightforward, very, very basic. Makes a lot of sense, really. Take an impact hammer, as such, subject it to a little hit, and the thing moves back and forth. By doing this, you're initially putting a velocity, a unit velocity of 1 on the structure. This is different than subjecting the thing to an initial displacement just by holding it back and then letting it go. And that point, the initial displacement would be 1. It essentially models the same thing. You can get natural frequency for the structure the same way. And of course, since you have the structure, and now we have all of our parts here that I've modeled, I can also model this up on top here by subjecting that to displacement or hitting that straight forward, or I can do the same thing with the base. Just take the clamp off of the base and then subject this to an impact or pull this back to subject to a free vibration. Essentially, the model is eventually going to indicate what the ideal what the ideal conditions for loft structure would be in terms of damping a natural frequency in an area that is subjected to high lateral loads, such as California or the West Coast in general. Now, this could also model other things such as attic design, or even the bottom part of the structure, if cut off from the top, could measure mezzanine design. But overall, it's by changing parts of this model, such as the stiffness of the plexiglass. I have 2 layers of plexi in here. If I take one off, that's going to decrease the overall stiffness. I can change the height of the loft, which I will do here in subsequent tests. Instead of having about a 10-inch high plexiglass wall in here, I'll probably have a 20, which will probably go 5 inches up and 5 inches higher up and 5 inches lower below. And then I'm also going to put in a vibrational motor in here in the middle of the structure to show and indicate what this would be like if actually subjected to live loads. Since the majority of loft structures are living quarters, they're going to be subjected to a lot of live loads. And so I want to be able to indicate those loads or replicate them with some vibrational motion which is induced in the vertical direction. Live loads would be anything such as a bed to a person to a bathroom, anything, or sorry, not a bathroom, but like toilets or something that could be there for the short stay, but not for the long duration. Something that you can move over a course of time. Yet even a toilet, a toilet could move depending on how the house is configured. It might be configured a different way. So there are a lot of things to consider in this, and this is the beginning of the test, and hopefully at some point I will be able to model all 16 different types of loft structures I have just by varying the thickness and whatnot, and then I'll be able to come out with the ideal dynamic response and ideal design for a loft structure given all of the responses that I find with the impact and free vibration tests.